This video is on the chapter of vectors in vector spaces, and we defined along these last videos the concept of norm or length of a vector. So the normal length denoted this way is the non-negative square. Okay, so at the end of the day, this, okay, of course this cannot be negative. Okay, so non-negative square root is the square root of u times, where this times is the inner product. Okay, it is defined this way. So you pick the components one by one. It will be u1 squared plus u2 squared plus etc. till the last component un squared, the square root of all this. Okay, so now we are going to show some properties of the norm. So any norm in a vector space Rn will satisfy these conditions. 1. The norm of a vector will always be greater or equal to 0, and the norm will be 0 if and only if the vector is 0. Please check one of the previous videos for the proof for this. Second property, k, a scalar k times a vector u, the norm of k times the vector u will be the absolute value of k times the norm of the vector u. And third property, the module of u plus v is smaller or equal to the module of u plus the module of v. Okay, if you check the previous video, you already proved this. This is, check the previous video for the Minkowski inequality, also known as the triangle inequality. And this one is more or less, this one is proved in one of the very old videos, where I proved something like the same proof as proving that minus u. Okay, but here there are modules, so I think we have to prove this one. Okay, let us do the proof. So what is, we want to prove this, right? The norm of k times u. But I already used this trick a couple of times. I'm going to use the square of this. Okay, so this spares me to use a lot of square roots. Okay, so basically, according to the definition, right, that would be k times u, that would be the norm of u, so that would be k times u squared, k u squared, etc. Okay, so I'm going to take the square root from here and put the square here. Okay, and what is this? Well, this is k squared u1 squared, k squared u2 squared, plus k squared un squared. Well, I can factor k squared, right? So I'll get k squared times u1 squared plus u2 squared, etc. till un squared. But what is this? This is nothing else but k squared times, and here we have the u norm, right, squared. So this equals to this. Okay, we should take the squares, right? So this k u squared equals to k squared u squared. We take squares, right, and the squares disappear, and this concludes the proof. what I meant here with this minus u is I wanted to add another proof for this. It's a very classical proof that says prove that the module of minus vector u is equal to the module of vector u. So the proof, you just used what we just used with this lambda, right? And just replace lambda, because at the end of the day minus u is nothing else but minus u times u. Okay, and we proved in the previous video that minus u times u, since this is a scalar, is equal to the absolute value of the scalar times the norm of u. Okay, so and this is absolute value of 1 times u, right? And this is nothing else but the norm of u. Okay, so we just proved that this is the same as this, right? So we proved that this is equal to this, as it was asked, and this concludes the proof.